cross product of two three-dimensional vectors. So we've talked about the dot product of vectors, and you can take the dot product of any two vectors of the same size, whether they're two-dimensional, three-dimensional, four-dimensional, whatever. The dot product is sometimes called the scalar product because the result is a scalar. So today I'm going to talk about the cross product. This, like old school multiplication symbol, is standard notation for the cross product. It is only defined for three-dimensional vectors, so you can't take the cross product of like a two-dimensional vector with a two-dimensional vector or a four-dimensional vector with a four-dimensional vector. So it has to be vectors that have exactly three entries. So the cross product, I'm going to do the cross product, compute the cross product using the idea of a determinant. So I'm going to have to mention that we have these vectors. I is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. So these are what they call the standard basis vectors for R3. They're lovely, and you can build vectors in R3 as a linear combination of these guys very easily. So if you wanted to say the vector 5, negative 2, 3, you'd take 5 times I, negative 2 times j, and 3 times k. So I am going to define the cross product as a determinant, and it's going to be the determinant of a vector. This is a little bit of an abusive notation because the first row in my matrix that I'm taking the determinant of is going to consist of these three vectors. So this is a little weird because we have vectors as entries of our matrix instead of numbers as our entries. Then I'm going to put the entries of the first vector in my cross product in. So 1, 3, negative 2, and then the third row is going to be 0, 1, 5. So I'm taking the determinant of this 3 by 3 matrix just the way we took determinants before. So I'm going to get the I times the determinant of this 2 by 2 matrix. So 3, negative 2, 1, and 5 minus j times the determinant when you get rid of the first row and second column, which would be 1, negative 2, 0, 5 plus k times 1, 3, 0, 1. So remember that second, it's a plus minus plus. And so we're going to have I times 15 minus a negative 2 is 15 plus 2 is 17 minus j times 5 minus 0 is 5 plus k times 1 minus 0 is 1. And so what I have is 17 times I, which is 1, 0, 0, minus 5 times j, which is 0, 1, 0, plus 1 times k is just k, which is 0, 0, 1. And so we end up with the vector 17 minus 5 and 1. So what we've done there is we've computed the cross product 1, 3, negative 2, cross product with 0, 1, 5 is equal to 17, negative 5, and 1. And what is handy about the cross product is if you look at the dot product of 1, 3, negative 2 with this vector that we got by taking the cross product, you get 17 minus 15 minus 2 is 0. What does that mean? It means that this vector and the cross product are orthogonal. And similarly, this vector will be orthogonal with the cross product 0, 1, 5, and 17, negative 5, 1. If you take the cross product here, you're going to get 0 minus 5 plus 5 is also 0. So the fact that the dot product here is 0 and here is 0 means that this cross product is orthogonal to these two factors in the cross product. So that's what the cross product does. It takes two vectors in R3 and it gives you a vector that is orthogonal to both of them, that is perpendicular to both of them. This can be very handy. Now, if you don't like this determinant method for computing the cross product, what you can do, and if you don't like it and you're good at memorizing formulas, you can use a formula, which is very easy to derive. So here's a formula for the cross product of two vectors. You'd have, if u is u1, u2, u3, and v contains the components v1, v2, v3, you'd have u cross v is equal to this thing. Now, I went ahead and just computed it in the general case using the determinant. So you can decide for yourself how you want to compute cross products. If you want to memorize this formula and use it, that's fine. If you're like me and you don't have a great memory for memorizing formulas and you don't want to use it, then you can use the determinant thing. And the determinant thing is very easy to remember, and it uses material that we know. So let's use a cross product. So let's suppose, I think this is a problem that was off the homework from last time. Let's suppose you want to find an equation for a plane that contains these points, and you want to find this equation in point normal form. So if you remember the point normal form, if you have a normal vector, and you dot that with a vector that you make from a point, that's going to be equal to the normal vector dotted with let's say x, y, z. So we want to use this form of the point normal form of the plane. In order to do that, I need to find a normal vector. Okay, so what I can do is I can find two direction vectors. So here's my direction vector 1 and direction vector 2, and I can take the the cross product of those two, and that will give me the normal vector to the plane. So I need two direction vectors, and it doesn't matter which two you choose. I'm going to go from this point to this point, so I'm going to get 4 minus 1 is 3, 0 minus 1 is negative 1, 2 minus 1 is 1. So that's one direction vector. The other direction vector, I'm going to go, say, from here to here. So I'll do 4 minus 0 is 4. What am I doing? 4 minus 0 is 0, minus 1 is negative 1, and 2 minus a negative 1 is 3. So I can compute, so this is, I have my plane, and here's my one direction vector, my other direction vector. If I compute the cross product of these two things, d1 cross d2 is equal to, is going to be equal to the normal vector. A normal vector. There are actually two. There's one coming up and one going down. It doesn't matter which one you use. So I want to find the cross product there. Again, you can use the formula that I showed you just now, or you can use the determinant. I'm going to do a little bit of a cheaty shortcut when I want to compute a cross product. What I do is I write the vectors on top of each other. 4, negative 1, 3. And then if you imagine doing that determinant method, you'd get I times this matrix, the determinant of this matrix, negative 1, 1, negative 1, 3. And so you're going to get negative 3 minus a negative 1 is negative 3 plus 1 is negative 2. And then you're going to get the j, so that's going to be the negative of whatever I get when I take the determinant of the matrix that you get rid of this middle column. So it's going to be 3 times 3 is 9, minus 4 is 5, so you're going to get a negative 5 there. And then it's going to be k times 3 times negative 1 is negative 3, minus a negative 4 is negative 3 plus 4 is 1. And then to check and make sure this really is normal to this plane whose equation you're looking for, you just take the dot product. The dot product of d1 with this thing is going to be negative 6 plus 5 is negative 1 plus 1 is 1. And you take the dot product with this vector, you're going to get negative 8 plus 5 is negative 3 plus 3 is 0. So this is a normal vector. Is negative 2, negative 5, and 1. And so the plane in point normal is, drum roll please, you're going to get the normal vector, negative 2, negative 5, 1, dotted with x, y, z is equal to, you take the normal vector, negative 2, negative 5, 1, and you dot it with a vector that's made out of any of the points that you want to. I'm going to use this one just because it's got the nicest numbers in it. And so here's the plane in point normal form. is beautiful. And then of course from there you can get the plane in general form by just computing this dot product and this dot product. So you'd have negative 2x minus 5y plus z is equal to negative 5 minus 1 is negative 6. And it's a good idea here, once you get the plane in general form, to check and make sure the points really do satisfy this equation. So if I plug in x equals 1, y equals 1, z equals 1, I better get 6. So if I plug in x equals 1, I get negative 2, y equals 1, I get negative 5, z equals 1, I get negative 7, plus 1 is negative 6. And similarly here, if I plug in negative 4, 0, 2, I'd get negative 8 minus 0 plus 2 is negative 6. And the last one's probably going to satisfy it because that's the point I used as my vector over here. But we can check. So you're going to get 0 minus 5 plus 1, minus 5, minus 1 is negative 6. So this equation really is satisfied by all three of these points. So this really is an equation for the plane that contains these 3 points in general form. And this again is point normal form. So that's it. Cross products. Okay, very good.